In this scenario, I've opened up the file stranded client-side.pcapng, and it's the first of two packet captures we're going to analyze to figure out the issue we're encountering. In this case, we have a network that has a headquarters and then one branch office that's being worked on that's relevant to this scenario. And that's a pretty common scenario across many networks of really any size, as you'll have branch offices connecting back to resources that are maintained at a headquarters office or at one single site. So we have some techs who are doing some work at the branch office, and all of a sudden they realize that in the scope of the context of the work they're doing, that users in the branch office can no longer access an application server that's housed at headquarters. Users on the network can still access the internet, but they cannot access this application server that's housed on the corporate network at the headquarters. So that's what we're trying to figure out. Now, to capture packets here, we're going to start with a client. So in this case, an individual client in the branch office who's trying to access that application, which is what we're looking at in the first packet capture we have opened here, stranded client-side.pcapng. To communicate with the application server, once again, let's think about what we need to do that. We need to be able to talk to our router, since we're routing from the branch office network to the remote network. And we also, in this case, we assume that maybe we're talking to the application server via some type of DNS name. So we may need an IP to DNS mapping to figure out what the IP address is. And then hopefully we have a path to that via our routers. So we only actually have a couple packets here. So there's some interesting things going on. Let's start by dissecting those. First of all, we see we have 172.16.16.101, which is our client in this case, and 172.16.16.251, which is our local DNS server in the branch office. And you can find these by looking at the network map that was provided in the scenario. That's how we know that's what these things are. So in this case, we see the client making a DNS request to the local DNS server on the branch network, and that's reasonably expected. It looks like we're making a standard query for the DNS name of app server. App server is the application server that's located in the central headquarters office that we want to connect to. That's the web application that we need to connect to. So we know that the connection is being initiated fine on the individual client workstation. The software is probably working right. But in order to connect to that server, it needs to find the IP address for it because it only has the DNS name. Now, hopefully we would see a response to this query with answers to the question being asked, but instead, the second packet tells us we have a server failure, and that's not what we want to see. We can look down here at the bottom and we see we have the question we've asked, but we don't see any answer resource records provided, just the query for the A record for app server. So something's clearly not working here. From the client perspective, we initiated the DNS query, but we did not get an acceptable response back. And that's really all we have to go on the client side. That's it. So to investigate this further, we need to look somewhere else. And I think the best case to look at here would be able to look at the DNS server in the branch office. It's who's receiving this request. And if you remember how DNS works, is it works on this concept of recursion. And we also have the ownership of zones that are existing across a hierarchy. In the case of our organization, we have a slave DNS server in the branch office, which connects back to a master DNS server back at the headquarters office. So there's a chance there may be some type of issue there. To figure that out, we need to pivot to a different capture file and actually look at packets captured from the branch office DNS server, which is what we're going to do next. I've now pivoted over to the stranded branch.dns.pcapng file, and this is actually a capture that was taken on the DNS server at the exact same time as the previous capture we just looked at. So we're getting the same sequence of events, but from a different perspective. So with that said, if we look at the first two packets here, they're going to look really familiar. They're the same two packets we've already seen. We see that we have the incoming request from the client at 172.16.16.101 to the device we're capturing from now, the DNS server, which is 172.16.16.251. We see that request come in, and then we see the response being sent back, which was that server failure we saw. Now, the only other packet we have to go on here is packet 3, which is interesting because this is actually a TCP packet sent over port 53. Now, remember that DNS generally uses UDP, but it does use TCP for a few specific functions. One of those was when a response was larger than a greater size, and one of those was for zone transfers. Now, the former isn't really relevant here because we don't have an issue where the response is too big, or else we would see truncation occurring, and then things would switch to TCP, and that would be no problem. We'd see a request, TCP request coming from the client. Instead, what we see here is rather interesting. 172.16.16.251 is the branch office DNS server. We also have a new address introduced here, 172.16.16.250. If you look back at the network map, that's actually the primary DNS server for the organization, which is also housed in the corporate network segment. So why would our slave server be trying to connect to our master server via a TCP connection? Well, the answer is the second scenario I mentioned just a second ago. It's a zone transfer. The DNS zone information that the slave server needs is contained on the master server, and it has to request that information. It has to request that zone transfer, which is what we see the start of right here. We see the slave server, which is 251, communicating with the master server at 250, and it's a TCP SYN packet on port 53, but we don't ever get a response, and that is where our problem is. In a normal scenario, our SYN would be met with a SYN ACK. We would close with an ACK to set up the communication channel, the TCP session, and then we would see DNS traffic flow, and we would see a request, either a full or partial zone transfer, an XFR or an IXFR to indicate a zone transfer, and then you would see DNS data flowing back from the master server to the slave server. But we don't see that here. And because that's the case, that means our client can't actually get the information from the slave server it's configured to look at. So that's a problem. Perhaps if it was configured to look at that master server, it may be able to get the information, but just looking at the slave server, it can't, because the slave server has not yet transferred that information from the master server. So how could we troubleshoot this further? Well, we could do what we just did. We just moved from the client to the branch DNS server, and we could do that again by moving from the branch DNS server to the central or master DNS server at headquarters. However, you'll notice I didn't include a packet capture for that specific environment. You want to know why that is? It's because there were no packets to include. In this case, the SYN never reached the destination. If there were, if we had seen that, we know that maybe there was a problem on that master server that's prevented it from responding, or the response didn't come back. But in this case, the SYN packet from the slave server to the master server never made it. That tells us that the problem lies in between the branch DNS server, the slave server, and the master server. And since we've just set up this new branch office, that maybe makes sense, right? There are a couple of routers at play here, and maybe the case was we simply didn't remember to put a rule in that allows TCP port 53 access from the branch office to 172.16.16.250, which is the most likely scenario in this case. So hopefully that makes sense. We got through a couple of hops here, but you really want to make sure you look at that network diagram so you understand what's going on. In this case, we have a DNS server from a client to we have a DNS query from a client to a DNS slave server. The slave server doesn't have the records it needs because it can't communicate with its master server, and that breaks down the whole process. So in this case, DNS, an application layer protocol, was the source of the problem, or at least was where the problem manifests, I guess is better to say. It's where the symptoms manifest, and the source is actually a connectivity problem between our slave and master DNS servers. So you can easily see how DNS could create an issue like this, since our name to IP address mappings are so important. Now, if the client had been configured to communicate with the application server via IP address, that might have worked, assuming the proper firewall rules were there. But in this case, the communication broke down, and we're unable to get to where we need to be, but we at least know where that problem lies and how to fix it now.